Set a glass of water on a table near the top of a modern cruise ship, and it behaves exactly like it's sitting inside a building on dry land. Around that glass, thousands of people are walking down corridors, swimming in pools, and eating hot meals, operating completely under the assumption that their environment is perfectly stable. Looking at this cross-section of a ship pivoting on its center axis, we can see why those high passenger decks pose a unique physical challenge. As a ship travels through waves, it naturally tries to roll. Because the upper decks rise so far above the waterline, a rotation of just a few degrees deep down in the hull translates into massive sweeping arcs from side to side at the very top. The hull can easily endure those angles and remain seaworthy, but a passenger thrown across a dining room cannot. Safety and comfort are related, but they are entirely different engineering problems. To solve the safety problem, we have to look deep inside the hull. Down here, engines, generators, and heavy piping systems are concentrated as low as possible to anchor the vessel's center of gravity. This animated diagram shows how that dense weight interacts with the water to create basic stability. When a wave tilts the hull, the shape of the underwater section changes. The downward pull of the heavy machinery and the shifted upward buoyancy of the displaced water create a turning effect, forcing the ship back toward upright. But basic stability creates its own mechanical flaw. A massive hull snapping back toward center generates momentum, causing it to overshoot the midpoint and roll the other way. However, if the timing of incoming waves matches the rhythm of that natural oscillation, each new push compounds the motion. The entire vessel might be in zero danger of capsizing, while the internal environment violently swings back and forth. Basic buoyancy alone cannot stop this pendulum effect. Therefore, to make the upper decks inhabitable, the ship has to actively extract kinetic energy out of every single roll. The first layer of defense requires no computers or moving parts. Running lengthwise along the lower exterior curves of the hull are metal plates called bilge keels. When the vessel tilts, these plates are forced sideways through the surrounding water. The sheer density of the ocean fights that movement, shearing off curling vortices as the plate drags through the sea. Creating those vortices requires effort, and that energy is drained directly from the ship's swinging motion, making every roll physically harder to continue. Passive damping works continuously, but it only reacts. It cannot predict the sea or actively push back against an incoming wave. For active defense, passenger ships deploy pairs of stabilizer fins near the middle of the hull. They are shaped like aircraft wings and function on the exact same principles, but instead of generating lift in the air, they generate it in the water. To see how they work, look at this diagram of the ship's control loop. As a physical wave strikes the hull, an onboard sensor immediately measures how far the ship is tilting and detects the exact speed at which the rotation is developing. That data feeds into a controller, which calculates the exact counterforce needed. It then commands heavy hydraulic machinery to rotate the fin's angle against the forward flow of the water, generating an opposing lift force to cancel out the wave. Position sensors instantly confirm the fin's exact angle, feeding that data back to the controller. Because the sea is always changing, the system measures the result, recalculates, and corrects the next command in a continuous cycle. When you walk across a steady floor at sea, you are feeling the physical result of this endless underwater math. However, conventional fins depend entirely on water flowing across them. As the ship's forward speed decreases, their ability to generate lift drops rapidly. This cross-section shows an alternative method used when the ship slows down, the anti-roll tank. By pumping or shifting precise volumes of liquid from one side of the interior to the other, the ship uses its own internal mass to perfectly offset the external tilt. Regardless of the mechanism, physics exacts a toll. Extending large fin surfaces into the water increases drag, and overcoming that fluid resistance requires burning significantly more fuel. Because of this energy cost, the control system never tries to erase every single trace of movement. It calculates the exact minimum reduction required to protect the interior without wasting massive amounts of power. Roll reduction is a strict operational necessity. A cruise ship is a moving city. Without stabilization, crew members handling hot food, Technicians working with unsecured machinery and medical staff operating equipment would face severe, constant hazards. The system preserves the ship as a functional human environment. As fuel, fresh water, and supplies are consumed over a voyage, the ship's overall weight distribution changes. Over slow timescales, engineers pump ballast water between holding tanks to adjust the draft and keep the hull in its optimal operating condition. Higher up, the officers on the bridge execute a macro-level strategy. By continuously monitoring weather and wave patterns, they intentionally alter the ship's speed and heading. Changing direction changes the angle at which waves strike the hull, keeping the vessel away from frequencies that would overwhelm the mechanical systems below. The ultimate engineering objective is managed motion. The layers of design, machinery, and navigation aren't fighting to make the ocean perfectly still. They are working together to keep the ship's movement within a tolerable, controlled range. That passenger calm doesn't exist because the ship is simply too large for the ocean to move. It exists because deep below the waterline, an active, hidden machine is constantly measuring its own role and pushing back against the sea.